Welcome to Digital Signal Processing Lab, and in this video we are going to conduct another experiment. So the objective of this experiment is written over here. You can read it out. So a discrete time system is described by the difference equation, and that equation is yn minus 0.5 yn minus 1 equals to xn. And the system is initially at rest, and we have to obtain the impulse response and step response of the system from the given difference equation. So this is our objective, and we have to implement this particular problem on MATLAB. So first of all, we have to look at, because we have to calculate the impulse response and step response. So we first look up how these two things can be calculated. Okay, so first of all, we have to see this is given as the system is initially at rest. So it means that if we don't apply any input, okay, the output should be 0. Okay, so because we are talking about the unit step response and impulse response, so normally if we talk about the impulse, means xn equals to delta n, that time we know that this delta n will be defined only for n equals to 0. And for n less than 0, the input will not be available, and therefore this yn is going to be 0, right? So because it is initially at rest, so this response is for n less than 0 for all these values of -1, -2, -3. This response, which is yn, and this yn is going to be 0. Okay, so that we have to remember, right? So if we are applying this delta function as the input to this particular differential equation, okay, this particular difference equation, sorry. So in that time, this response yn is also referred as hn, right? Because we are applying the input as delta function. Therefore, this response is normally regarded as the impulse response of the system, and it will be denoted by hn, right? So here we are having this plot for delta n. You must be aware of that, because in the delta n, mathematically it is equals to 1 when n equals to 0, and for all the other values of n, this value will be 0. So here we can show that this is your all 0 samples, right? Here again it is 0 samples at n equals to 0. This delta function will be taking a unity value. So now we have to see how this response yn can be calculated when we are applying this delta function as the input, right? So here I have calculated, here we can see this response. Okay, so here we can see this responses. So because I have already implemented this expression. Okay, you can see this in the table. What I have done is I have just taken this differential that difference equation, okay, that was defined as yn equals to, means yn minus 0.5 yn minus 1. So that part I have shifted to the right hand side, and then this expression can be modified like this. Okay, yn will be becoming equals to xn plus 0.5 yn minus 1. And here I have calculated yn minus 1, and here I will be mentioning about the input sequence. Okay, when we are changing the time index from 0 to 9. For the simplicity, I'm not considering any negative values of n, because we know that the system is initially at rest, and therefore the response yn is going to be 0, right? So if we substitute n equals to 0, as we can see, this delta function will be taking the value equals to 1. So therefore, this input xn, I am showing it to be equals to 1. So here we can see this calculation if we substitute n equals to 0, because in this difference equation, we are having this element, okay, yn minus 1. So if you substitute 0 in this yn minus 1, then we will be getting y minus 1 we have to show, because I have already shown that because the system is initially at rest, y minus 1 will be equals to 0. Okay, so I am just substituting this value from the given condition, right? Now we have to calculate this response yn. So this yn we can calculate by substituting the values of xn and yn minus 1. So I have calculated yn minus 1 equals to yn minus 1 in this particular column. So it is y minus 1. It is coming for n equals to 0. This value will be equals to 0. And this xn is equals to 1. So if you substitute here, it will be 1 plus 0.5 multiplied with 0. So ultimately this y0 that we are going to get is equals to 1. Okay. Again, similarly, if when n equals to 1, this xn is 0, we can calculate because we have already calculated this. If you substitute n equals to 1, this value will be coming out as y0, and y0 we have already calculated in the previous step. So this y0 is equals to 1. Okay. Now again, we can update the y1, right? So that will be updated by substituting this y0 that we have calculated in the previous step and then the current input, right? So if you do that, this value is equals to 0 and this value is equals to 1. So it is 1 divided by 2. So value is remains 0.5. So the similar steps we have to follow for all the rest of the inputs, okay, for different time index when it is varying from 2, 3, 4, 5 up to 9. So for the simplicity, I have just taken up to 9. You can also take the more values of n, right? So this way you can just try to verify all this data, okay? This way you are going to get this particular impulse response of the system. Similarly, if you are interested in to calculate the step response of the system, okay, so normally when this input is xn equals to un, your unit impulse unit step sequence, in that time this yn is normally denoted as sn, right? So here we can see again very similar discussion, okay. So this is the our unit step sequence that we are applying to this particular system. So we know that because it is un, so un will be 0 for n less than 0. Okay, so for all less than 0 values, this un is going to take this sample to be 0. Okay, these values will be 0. And for n equals to 0 and greater than 0, this value is going to be 1. Okay, so this is the mathematical definition of your unit step function. So this way we have defined this our unit step function, right? So again, we have to do the similar analysis. Okay, we are just taking this time index. Again, we are taking the xn because an xn for n equals to 0 and greater than 0, this values will be going to be 1, 1, 1, 1, 1. So that's why I am substituting here 1, 1, 1. Again, you have to just follow the same difference equation. You can calculate y0, y1, y2, y3, y4, and so on. Okay, so that we have to calculate, right? So just try to verify these results. You will be able to get these values. Okay. So now let me tell you how this two responses can be implemented on MATLAB. Okay, so let me go to the MATLAB. So here I have already written this code onto MATLAB. So here you can see that we have to actually we have to find out the impulse response and the step response of a given system. So here is the first line that I have written. So it is CLC to clear the command screen, command window, and this is clear to remove any previously generated variables from the workspace, right? So first of all, we have to create the input sequence, right? Input sequence for your unit impulse or step unit step functions, right? So for unit impulse, as we already I have shown you this picture, okay, because we have to generate this type of impulse, right? So at n equals to 0, the first sample should be 1, and then the rest of the sample should be 0. Okay, we are not interested in this part, okay, because for n less than 0, the output of your system is going to be 0 because it is initially at rest. Fine. So similarly, what I have done is I have created the a unit impulse input array. So here x equals to the first element would be 1, and then I'm just putting next 9 zeros. Okay, so this particular array of x is taking total 10 samples, in which the first sample is 1 and the rest of the samples will be 0. Okay, so I have created one more variable. Okay, means I have already created the unit step input array also. Okay, so that for that particular creation, we have to follow this particular command. Okay, once, right? So if you write once, it will be creating 1 row and 10 columns. So there will be total 10 such elements. Okay, and all the values of the element is going to be 1, right? So this way I'm taking 10 elements in this particular X, and also in this particular X, total 10 elements, right? So right now I have just commented this line because we are interested in to calculate the unit impulse response, right? So this line is commented, right? So now how to implement this difference equation, that we have to look at. So if you see, in the MATLAB, normally the index, okay, for any element will start from 1, okay? So we cannot have any element from like y0 or y minus 1. So that way we cannot define in the MATLAB. So there may be a first sample to second sample, third sample, but we cannot have any 0th sample, right? So here the sample index, okay, that should be start from 1. So that we have to take care, right? So here I have already calculated the y1. Okay, you can see I have already calculated this y1 here. So if you see this y1 in the case of calculating the unit impulse response, you can see this y1 value. Okay, I mean to say here it is y1 means it is reflecting the y0 value. Okay, remember this point, because we cannot in the MATLAB we cannot define y0, right? So the first output, okay, the first output in the MATLAB will be denoted as y1, right? So this y1 is equals to 1, that I have already calculated from this expressions, right? So now the same thing I have defined here. Okay, this y1 is equals to 1, and now we have to implement the difference equation. So I'm just writing this for loop. So in this for loop, you can see this for loop is means it is changing from this particular variable k is changing from 2 to 10. Right, so we have to write the same difference equation. Okay, so there we had this variable n, but I'm just putting this variable name as k. So now yeah, just writing this the same difference equation that I have shown in the slide. So yk is equals to 0.5 multiplied with yk minus 1 plus xk, right? So why we are starting with k equals to 2? Because if you start this loop from k equals to 1, because it is k minus 1, that time this will become y0. And as I said that in the MATLAB, we cannot have the any element index equals to 0. Okay, it should start from 1, right? So that's why I will started from k equals to 2. So once you will be taking k equals to 2, right? In the time index value, it is corresponding to n equals to 1, that you remember. Okay, while plotting, we will be just shifting it a little bit, okay, by one element, and then we can do the plotting, right? So it is k equals to 2. If you substitute, we are calculating here y2. Okay, we are calculating y2, fine. But if you see the same thing in this slide, this k equals to 2 means we are calculating right now y1. Okay, because your n index will be equals to 1. So this way we are actually doing the calculation, right? The same expression we have to implement, right? So we are just writing the same expression. We have to complete this loop, okay? And then I am defining this time index variable n equals to 0 to 9. And then we can go on plotting, right? So stem function we have to use for discrete plotting. So if you execute this code, okay? If we execute this code, we will be able to see this output. Okay, so here you can see this output, right? So because I have created the time index variable from 0, okay? So that's why it is showing from 0, 1, 2, 3, and up to 9. Okay, so here you can see this definition of it. Okay, so this definition I have defined from n equals to 0 to 9. And therefore it is coming like that. Okay, so here you can see and you can verify this output from the table. Okay, so here you can see this is 1. Okay, here you can see this value is coming out as 0.5. Then here you can see this value is coming as 0.25. Okay, 0.125, and then so on. Okay, so that values you can easily verify. So this is our impulse response of the system, right? So this way we can get the impulse response. Now, if you want to calculate the step response, I will be just commenting this line, okay, because this axis corresponds to unit impulse input array. Okay, so I'm just commenting this line, and I will just remove this comment. Okay, so once I will remove this comment, then this axis equals to corresponding to unit step input array, right? So now if you execute this code, then we are supposed to get the output corresponds to step input. Okay, so this is the response that we can see. Okay, this is the response, right? So here you can see this magnitude is 1 and this magnitude is 1.5, 1.75, okay, 1.875 and so on. So that you can verify this all data, okay, from this table, okay, that you can calculate manually, okay, from the given difference equation, and then you can verify all this data. So this way we can easily calculate the impulse response and step response of the system, okay, from the given difference equation. So that we can do. One more function in the MATLAB command that we are having is normally we avoid this using the for loops, okay, normally in the MATLAB, okay. So we are having another function in the MATLAB which can easily get this response, okay. So that function is filter function, okay. So we have to use the filter function and then we can easily get this response, okay. So how to use this filter function? So first of all, we have to look at this explanation, okay. So because we are having this difference equation, yn equals to means yn minus 0.5, yn minus 1 equals to xn, okay. So this particular expression, we can apply xn equals to delta, and that time this yn will be converted into hn, okay, impulse response. We can denote it by the hn, right? So if you take the z transform of this particular expression, you will be getting hz minus 0.5, z to the power minus 1, hz equals to 1, and the final hz that you are going to get is 1 upon 1 minus 0.5 z to the power minus 1. So this is the final hz that you are going to get. So this hz is nothing but it is the ratio of output upon input, okay. Z transforms, right? Output upon input Z transform, which is normally called as the transfer function of the system. So normally if we implement a filter with this filter coefficients, okay, this is our numerator polynomial, okay. So here we have this numerator polynomial and this is our denominator polynomials, right? So if we implement a filter with this polynomials, this coefficients, then if we pass the any signal, right, any signal, whether it is a delta n or if it is a un, okay, step unit step function, unit step function, then we are going to get the corresponding outputs, right? So basically we have to use this numerator coefficient and denominator coefficients, or otherwise we can also say that if we compare this particular expression from this generalized expression, okay. So here we have this coefficient a to the power k, and k is varying from 0 to capital M, and here in the right hand side, this k is varying from 0 to capital M, and then we are having certain coefficient. If you make the comparison of this generalized expression, difference equation, okay, from this given expression, okay, you can find out that here just for this xn, okay, we are just having this k value here. It is just varying from only k equals to 0 only, right? So we don't have n equals to 0. It is just only one time, right? But in this case here it is k is varying from 0 to 1, right? So here we are going to get this two coefficients a 0, okay. So it will be a, and then the next means the coefficient that we are going to get is 1 and then 0.5 minus 0.5, okay. So this coefficients I have written here, okay, 1 minus 0.5. In both ways you can understand whether it is this polynomials, okay, numerator and denominator polynomials, or otherwise we can also compare it with this given difference equation, and then you can find out what is the values of a's and b's, right? So once we are getting this a's and b's, it is quite simple. In the MATLAB we have to just use this filter function, okay. So we have to use this filter function. So this is the filter function, here you can see. So here we have to substitute this b and a coefficients, right? We are defining the filter, right? So here I have already defined this coefficients, okay. B is equals to 1 and a equals to 1 minus 0.5, okay. So this is what we have to give, right? So we have to give this coefficients, and then we have to apply the input, and then directly we are going to get the output in this H. Okay, so filter function will give you direct output. Okay, so in that case, we have to we can avoid this all writing this for loops, right? And then we will be able to plot this figure. So we can make this comparison. Let me remove this comments first because this line was commented. So let me remove this comment. So now we can execute. Okay. So let me first close this window, figure window. Now, if we execute this code here, you can see this first figure here, you can see, okay, this is corresponds to the for loop that we have used. Okay. And this is your corresponds to filter function. Okay, and here you can see that we are getting the same output. Okay, you have to check all the values. Okay, all the values. So this second figure, this corresponds to your filter function, right? So this filter function can be used very easily, right? So again, you can see, even if you want to get the impulse response, because at present our input is corresponds to unit step function. So if you comment this line, okay, let me comment this line and then remove this line, okay, this particular comment, right? So now this is unit impulse input array we are applying. So if you execute this one, again, you can see we are supposed to get the same output. Okay, so this is corresponds to for loop, and this output is corresponds to filter function. So I hope you must have able to understood how to get this impulse response and a step response from the given difference equations. So keep watching this video and try to implement using the MATLAB. And if you have any queries, you can ask your doubt by sending messages to the comment box. So thank you for watching this video, and stay connected with the channels for more updates.